All right. All right, so if you watched the video that I had posted that pertained to chapter 24, let's just do a quick review of some of the reactions that you have to know from chapter 24. And let's try some practice problems so you'll understand the concepts very well. You know, the sugar that comes up the most in this chapter is D-glucose. And there's a reason why D-glucose is the most abundant monosaccharide on the planet Earth. If you take D-glucose, which is a monosaccharide, and you draw the Pyranov form, the six-membered ring form, I'm going to show you how to do that using my patented method, patent pending. When you do that, if you draw a chair form of this Pyranov ring, so here's the Pyranov ring. What I'm going to do is I'm going to draw the chair over here, and the chair form looks like this. I'll do my best chair. Not too bad, not too great. Okay, so this hydroxyl is pointing up. So that means it's at this carbon and it's pointing up. That means it's in what we call the beta position. If a group is pointing up on this carbon, which is called the anomeric carbon, if it's going up, it's beta. And if it's pointing down in this direction, it's alpha. So this is beta. If this hydroxyl is going down, so if we number here 1, 2, 3, 4, 5, 6, we number here 1, 2, 3, 4, 5. Where did I miss here? Oh yeah, I know where the other carbon is. It's supposed to be right here. There we go. So CH2, like that, OH. So this would be carbon 6 right here. So if we look at carbon number 2, it's going down. So on carbon number 2 in the chair, if something's going down, it's going down in equatorial. The next carbon number 3, the hydroxyl is going up. It would be up in equatorial. Carbon number 4, the hydroxyl is going down. It would be down in equatorial. And then in carbon 5, you have this group pointing up, so it would be up in equatorial, the CH2OH right here, and that's this right here. So the reason why glucose is the most abundant monosaccharide on Earth, and this would be beta D glucose, the reason it's so abundant is because everything is equatorial. This substituent is equatorial, this one is, this one is, this one is, and so is this one here. Everything is equatorial in glucose, especially beta D glucose. If you have alpha D glucose, then the anomeric hydroxyl is pointing down. So if I put this going down like this, this would be alpha D glucose, but that's not what was drawn in that Haworth projection. So there we go. That's why glucose is so common. It's just because all the substituents are equatorial. So again, I'm going to go over how to go from the open chain form to the Pyranov ring form with you. As far as drawing Pyranov rings, which are 5-membered rings, you might remember those from your biology class, things like ribose and deoxyribose. Those are 5-membered rings, which we call a Pyranov. I'm never going to ask you to go from a ketose like this and draw a Pyranov. The only thing you've got to be able to do is go from an aldohexose, draw a Pyranov ring, draw a chair, and back and forth. Okay, those are the things you've got to be able to manipulate. Just 6-membered rings. I'm not going to ask you to draw anything with a 5-membered ring. As far as the reactions of a sugar, of a monosaccharide, there's a bunch of kind of just one-off reactions here, just one step. Okay, so you know the first ones, or the first couple that I covered, these two here. The first one is acetic anhydride impurity, and what that does is it adds an acetyl group to every oxygen. So remember, an acetyl group, this AC, is the same thing as, it's like a methyl ester that you form on every one of those. So if you have OAC, you have a methyl ester on the end. And the reason you do that is to render the compound more soluble in organic solvents. The same thing here, if we add a methyl group to everything, it's like a Williamson ether synthesis, but instead of using a strong base like sodium hydride or something like that, we just use aqueous silver oxide, which is a weak base or not nearly as strong as sodium hydroxide, and iodomethane, and that just methylates everything. So we call that alkylation. The first one was acetylation. The next one is the formation of a glycoside. If you take a 6-membered ring, a Pyranov, and you treat it with an alcohol like methanol and HCl, what that does, and I'm going to go over the mechanism of this with you, with ethanol or something. What it does is it puts an alkoxy group at the anomeric carbon. Remember, carbon number 1 is called the anomeric anomeric carbon. There's something called the anomeric effect, which we don't cover in this course, but anyhow. So you end up putting an alkyl group on this oxygen, and then you go from having a hemiacetal to an acetal. Check this out. If you zoom in here, you can see that the anomeric carbon has a hydroxyl and an ether on it. That means it's a hemiacetal. Whereas when you put an alkoxy group on this carbon, you don't have a hemiacetal anymore. We have a carbon-oxygen-carbon and a carbon-oxygen-carbon. So we have an acetal. So an acetal at carbon number 1, we call that a glycoside. The next one is reduction to reduce the aldehyde at the top, because remember, what they have drawn here is the closed form, the 6-membered ring, the pyranose form of beta-D-glucose. But if you wanted to draw the open chain form, I don't have a lot of place to put it here. But again, I'm going to show you how to do this, how to go from the cyclic form to the open form. We have 1, 2, 3, 4. So you have a hydroxyl here, here, and here, here. You have these hydrogens, CH2OH. Then you have your aldehyde up here. We'll just abbreviate that as CHO. So what you're doing is you're taking this aldehyde, and with sodium borohydride and water, you reduce it to CH2OH. So you reduce it to an alcohol, and we call this an alditol. So this would be called an alditol. So number 4, reduction to form an alditol. The next one is just oxidizing that carbon that I have highlighted in yellow. We use bromine and water, and in the book it says that it's at a pH, a very specific pH, equal to 6. And so that oxidizes, again, the aldehyde to a carboxylic acid, and we call that an aldonic acid. So I'll scribble that in here. This is called an aldonic acid. And then if you really hit it with the big guns, which is nitric acid and water, and just heat it really hard, that's going to oxidize the aldehyde group that I have highlighted in yellow, but it will also oxidize this primary alcohol, and it oxidizes both of them to a carboxylic acid, and that's called an alderic acid. Alderic acid. So an aldonic acid only has a carboxyl group on the top, but an alderic acid is a carboxyl group at the top and at the bottom. All right, so those are kind of the one-off reactions that you need to know, all 6 of these. And then we have what are called chain lengthening and chain shortening reactions. The one on top is a chain lengthening process. We call this the Kiliani Fischer synthesis. So you can scribble that in here. I don't know about my spelling skills of these people's last names, but Kiliani Fischer. So Kiliani Fischer. And it's the same Fischer that invented the Fischer projection. But what happens here is that when you treat the aldehyde group with HCN, you end up making a cyanohydrin, and then that gets reduced to make a mixture of diastereomers. Now, they only differ at 1 chiral center. Does anybody know what you call it when you have 2 carbohydrates that differ at only 1 chiral center? They are diastereomers, but there's a special word that we use for it when they differ at the chirality of 1 chiral center. It's a word that starts with the letter E. Yeah, exactly. They're epimers of each other. Exactly. So that they would be, D-glucose and D-mannose, they would be epimers of each other. And then the other synthesis that you need to know is kind of a funny one, which is the Vole Degradation. I always thought both of these were interesting. And there's good reasons for these reactions, but Vole Degradation. It's just what I always found funny about Kiliani and Fischer is that you start with one thing and you always, or almost always, end up with 2 things. Whereas the Vole Degradation is kind of neat because you could take a mixture of 2 different things, you mix them together, do the reaction, and you only end up with 1 product in the end. So that's kind of neat. So Kiliani Fischer was HCN followed by a poisoned catalyst. This poisoned catalyst is hydrogen, and you've got this whole cocktail of palladium on barium sulfate and water. So this is a type of poisoned catalyst, just like the Lindlar's, but you know, a different structure for different reasons. The next one, the Volga degradation. This is a lot of steps. The first one forms an oxime, then you do a dehydration, and then you just treat it with base and do an elimination. But and I won't ask you the mechanism of either of these. Okay, I'm not going to ask you to start pushing arrows on either of these. There are some, you know, mechanistic arrows in the book, but that would never come up on an MCAT or anything like that. So don't worry about drawing mechanisms for either of these. Just make sure you know the chain lengthening and the chain shortening. So what I thought we would do now is, with the aid of the handout, is kind of go through a few problems in the book, and I can cover a lot of the concepts just by looking at a few problems. And I thought we would start with question 24.13. So I'm going to go over to a blank document. You're just going to have to bear with me while I read these. So the first one is, 24.13. And if you look at our textbook, if you have it open, 24.13 says provide a complete name for the following compound. So what we're going to do is we're going to draw this Haworth projection of this Pyranov ring. So we have our CH2OH group up here. We have our hydroxyl on the anomeric carbon pointing up. This hydroxyl is pointing down. This hydroxyl is pointing up. And this hydroxyl is pointing up, like that. All right. So remember, we start numbering on the anomeric carbon. 1, 2, 3, 4, 5, and 6. What we do is we're going to draw a straight chain like this. We're going to draw 4 lines horizontally. 1, 2, 3, 4. At the bottom, always put CH2OH. And at the top, we're going to put CHO. Remember that CHO is the same thing as writing out the entire aldehyde like this. It's just faster to write the condensed version. So I'm going to go back to the condensed version. Oops, that's not right. There we go. So there's the condensed version. We're going to start numbering at the top. 1, 2, 3, 4, 5, 6. So carbon number 1 only becomes a chiral center when you have the cyclic form. Carbon number 1 in the open chain form, so this is called the open chain form, is not a chiral center because this carbon is sp2 hybridized. So we go to carbon 2. Here's the rule. Anything that is pointing down, is going to end up on the right-hand side of the molecule, the right-hand side meaning this side over here. And anything that's pointing up is going to end up on the left-hand side. Okay? So watch. Carbon number 2, the hydroxyl is pointing down, so it's going to be on the right-hand side. Carbon number 3, hydroxyl's up. Carbon number 4, hydroxyl's up. So both of those are going to be on the left-hand side. Now, carbon number 5, where's the hydroxyl? Well, the hydroxyl at carbon 5 is the one that ends up cyclizing, right? It ends up cyclizing here to form the ring. So why did I put the hydroxyl here on the right-hand side? Could anybody tell me? Did anybody pick up on that from the videos? There's a reason why I put it there. I just kind of magically knew to put it on the right-hand side on carbon number 5.
Isn't that the beta position of the anhydride carbon?
It's not the beta position. Do you remember that in the book it talks about D sugars and L sugars? Does everybody remember that? It went on like D glyceraldehyde, L glyceraldehyde. So it's I'll show you, Karen. It's based off of glyceraldehyde. Everything starts with that. And again, you don't have to memorize the structure of it. It's not a bad idea. But D-glyceraldehyde is what all the naturally occurring sugars can degrade to. So this is called D-glyceraldehyde. There we go. So D-glyceraldehyde When you have D-glyceraldehyde, it means that the hydroxyl on the only chiral carbon here is on the right-hand side. Every sugar that we deal with in this class is a D sugar. Why do we only deal with D sugars? Because there's a whole series of L sugars. If you look at that handout, the only sugars that are on it, I'm holding it in my hand, the only thing on there is a D sugar, because D sugars are natural. Okay, they're naturally occurring sugars, D sugars. L sugars are not natural, and an L sugar, don't write this down, but an L sugar would have the hydroxyl on the left-hand side. So anytime you're drawing an aldohexose like this, the hydroxyl on carbon 5 will always be on the right-hand side. In fact, if you look at anything on that sheet, on that handout, the last chiral carbon, whatever the molecule is, the hydroxyl will always be on the right-hand side. So that's why I just magically put it there. Now that we've got the 4 hydroxyls in, we fill in our protons. So we put a hydrogen here, 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 and here. And there we go. So now we can go over to the sheet and we can pick it up. And I'm looking at it right here. I mean, I already did this one. But if you look at the sheet, you can see that this is D-galactose. So this is D-galactose. All right. Now, this isn't a question from the book, but what I want to do is take another sugar and show you how to go quickly from the open chain form to the pyranose form and the chair form. Let me show you very quickly how to do that. It doesn't take long at all. Let's say we had a sugar like, I don't know, I'm going to pick, let's pick, I don't know, let's pick D-gulose. So let's imagine we had D-gulose, and if I go over to the handout and look up the structure of D-gulose, it looks like this. So I have my 1, 2, 3, 4 chiral centers. It's a D sugar. So the last hydroxyl is going to be here. Then I have 1 here, 1 here, and 1 here. Okay. So now I fill in all my hydrogens because I want to be accurate. And now I'm going to teach you how to draw the pyranose form. Here's the rules. You draw a 6-membered ring and you put the oxygen in the top right-hand corner. Okay, that's step 1. Step 2 is your CH2OH is always going to be in the top left-hand corner. So you can put CH2OH like that if you want. If you want to just, use a partial bond line structure like that, that's okay. I'm going to leave it the way it was. So CH2OH. Now you have all the carbons. So we're going to number the ones in the chain. You start at the top. 1, 2, 3, 4, 5, 6. We start here. This is always carbon number 1, the anomeric carbon. Carbon 1, 2, 3, 4, 5, 6. Like that. Oh, I already had the name up there. Okay. So what we're going to do is we're going to draw beta D-gulose. So beta D-gulose. Not glucose. Gulose. There we go. Remember that this beta, that refers to the anomeric carbon. If it's beta, is it pointing up or down? Did anybody tell me that? I had a little mnemonic that I went over in that video.
Up.
Exactly, right? So if it's beta, it's pointing straight up like that. So, and the way I remember that is beta kind of looks like a butterfly. And butterflies fly in the air. Anyhow, let's erase that. So it's beta. Then I go to carbon 2. This is on the right-hand side. That means it's pointing down. The next carbon, the hydroxyl, is on the right-hand side. So it is also going to be pointing down. That on carbon number 3. I go to carbon number 4. The hydroxyl is going to be pointing up. And just like that, we drew beta D-gulose from D-gulose. When you go to draw the chair, what we do is the same thing. We draw a chair. We always have the oxygen in the top right-hand corner, like this. This never changes as well. You always have your CH2OH pointing up like that. I'll just leave it as the bond line structure because the chairs are hard enough to draw as is. Okay, so what we do on carbon number 1, the hydroxyl is pointing up, so it's going to be going up and equatorial. On carbon 2 and 3, both groups are pointing down. So on carbon 2, it's going to be down and equatorial. On carbon 3, it's going to be down and axial. So let's number these. 2, 3, 4, 5, 6. On carbon 4, it's pointing up, so it's going to be up and axial, like that. And just like that, we drew the chair form. So again, this is called the Haworth projection or Hayworth, depending on who you ask. And this is the chair form. So that is how you go from any of those aldohexoses, aldo for aldehyde, hexose because it's got 6 carbons in it. That's how you draw the Haworth projection and the chair. Any questions about going back and forth? The open chain form to the ring form, which is called the Pyranov form. Okay, let's try another question. Let's try 24.17. Scroll down here to 24.17. And 24.17 is in the same vein as what we just looked at. It says draw the open chain form. So draw open chain. Okay, and this is our chair. So I'll draw the chair again as neatly as I possibly can, like that. So we have our hydroxyl going up here. We have this here. We have a hydroxyl here. We have another one going straight down here. And we have one going down here. So now I want to draw the open chain form. I do the same thing. I have my aldehyde. I have my CH2OH. Always 1, 2, 3, 4 chiral centers. Like that. You can number the carbons. Anomeric carbon 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. The anomeric carbon, that hydroxyl, is not a chiral center in here. But then when I go to carbon number 2, this is pointing down. So, like I said, if something's pointing down, it's going to be on the right-hand side. So I've got a hydroxyl here. On carbon number 3, it's also pointing down. On carbon number 4, it's also pointing down. And on carbon number 5, well, I know it's a D sugar because we are only dealing with D sugars. Therefore, it's going to be on this side. Well, that is an interesting compound. All the hydroxyls are on one side. And that is D-allose. This is D-allose. Is everybody with me on the, a group is going down, it's on the right-hand side. A group is going up, it's on the left-hand side. Really, the only chiral centers you have to worry about when you're going from the straight chain to the chair are carbons 2, 3, and 4. That's it, because carbon 5 is always going to have the hydroxyl on the right-hand side because we only deal with D sugars in this class. Okay, let's take a look at another one. This is question 24.23. It says draw the product when each of the following compounds is treated with acetic anhydride in the presence of pyridine. And the first compound they gave us was alpha-D-galactopyranose. Now, I've already gone ahead and drawn the structure of alpha-D-galactopyranose from the open chain form because that's the only thing you would have, but I'm kind of going to skip that step. Galactose is probably one of those things that I have memorized. So alpha means this carbon's going down. Remember that in glucose, everything was equatorial. So equatorial, equatorial. The only difference between glucose and galactose, so this is alpha-D-galactose. The only difference is at carbon 4. At carbon 4 in glucose, the hydroxyl is going down, but in galactose, it's going up like that. So this is alpha-D-galactose. What I'm going to do is treat it with acetic anhydride and pyridine. Acetic anhydride just works as an acetylating agent, so it adds acetyl groups to every single hydroxyl. 1, 2, 3, 4, 5. You put a hydroxyl, an acetyl group on all of those. Let's redraw chair. So we have our acetyl group down here. We have another acetyl group here. Another acetyl group here. One going straight up here because this is galactose, and we have one on the primary hydroxyl. And that's it. That's the whole thing. There's two more examples in there, but they're the exact same thing. So make sure you know acetylation. All the hydroxyls get acetylated when you treat the carbohydrate with acetic anhydride impurity. Remember that AC2O is this compound. We looked at it in the carboxylic acids chapter. It's acetic anhydride. Very commonly used reagent in organic chemistry. It has a variety of uses. Next, I wanted to take a look at a question about a glycoside, as I promised earlier. So this is question 24.25. It says, when alpha D galactopyranose, which is the compound we just drew, is treated with ethanol in the presence of an acid catalyst, such as HCl, two products are formed. So we're going to take alpha D galactopyranose, that means the six-membered ring, and we're going to treat it with HCl and ethanol. And it says that we end up with two products. So two products. And then it says draw both of them and draw a mechanism for their formation. So if we go back here, this is alpha D galactose. You could call this alpha D galactopyranose as well, because this is the six-membered ring, okay? So you could draw it like that. You could draw it as a Haworth projection. It doesn't matter. They both mean the exact same thing or communicate the same thing. So what I'm going to do is I'm going to draw the chair because that's the way it's done in the solutions manual. And let's start by redrawing alpha D galactopyranose. It's the compound we just drew a minute ago. Alpha, so that means the hydroxyl is pointing down. Then these two are equatorial. On carbon 4, the hydroxyl is going up. It's axial. And then this is equatorial. So what we're doing is we're going to treat the molecule with HCl, and we're in ethanol as a solvent, ethyl alcohol. The first thing that's going to happen is we're going to convert the anomeric hydroxyl into a good leaving group. So we're going to do a proton transfer with our strong acid, and that is going to give us the protonated form. Which looks like this. So we're going to have OH2 plus. So now this is a good, very good leaving group. So it's going to leave. And we have two lone pairs on this oxygen, so it can help to eject this leaving group. And then we end up with a carbocation. So let's draw, we end up with an oxonium, actually. And you could draw the mechanism like this. You could just draw the loss of leaving groups. Let's draw the carbocation first, which is going to look like this. Carbohydrate chemistry will really get you practicing drawing your chairs over and over and over till you're very sick of it. So there we go, like this. So here's our carbocation, but we know that that has another resonance contributor. We could dump a pair of electrons in here. So let's draw the other resonance contributor. See if I can squeeze it in here. It's going to look like this, like that. And you get a double bond here. You've got a positive charge on your oxygen. This is the most abundant contributor because now everything has a complete octet. But what do we know about the molecular geometry of sp2 hybridized carbons, right? This carbon, the anomeric carbon, this one right here, that's sp2 hybridized now. So now my ethanol, which is my nucleophile, can come in and it can attack from the top face or the bottom face of the molecule. If the ethanol attacks from the top face, it's going to come in from this side. I'm going to put my lone pair back on here, and that's going to give me the beta anomer. Let's draw that like this. So it's going to be pointing up. And then after a proton transfer, I'll just put proton transfer at the end. You're going to end up with your ethyl here. So you have a glycoside. So let's put all these groups in like that. However, if your ethanol attacks and then you get a proton transfer, so ethanol, proton transfer. If the ethanol attacks from the bottom, like this, okay, I got two sets of arrows on the same molecule, but it'll have to do for now. Then you're going to end up with the alpha anomer. So let's draw the alpha anomer. We have the ethoxy group pointing straight down now. And everything else is the exact same. And these are called glycosides. When you have an alkoxy group at the anomeric carbon, these are both glycosides. Glycosides. All right. There we go. So that's why we get a mixture. And here we have the beta anomer because the alkoxy group is pointing up at the anomeric carbon. And here we have the alpha anomer because it's pointing down. There we go. So that's a little bit of mechanisms and how you can take something like alpha D-galactopyranose and you end up with a pair of compounds that are, we call them anomers. So these two compounds, since you have beta and alpha, technically they're stereoisomers, they're diastereomers, but the correct name, since they differ at the anomeric carbon, we say they are anomers. Anomers of each other. Anomeric center. If you Google search anomeric center, you'll find all kinds of cool information about anomeric centers. And there's a very famous book written by a Canadian chemist named Pierre de Longchamp, a French guy, and he wrote a whole book just about anomeric effects and stuff like that. So it's kind of, I think it's kind of interesting. It's not part of the content in this course, and we already have enough to worry about. So let's move on from there. I wanted to take a look at 24.27. This one's a kind of a straightforward problem. It just says draw and name epimer. So it says epimer of D-glucose. And I think it was Brianna who answered my question about epimers earlier on. So let's say we have D-glucose. So let me draw D-glucose. One I have committed to memory. And I always draw it the same way. So this is D-glucose. And what Brianna said is that an epimer is a diastereomer that only differs in one stereocenter on a carbohydrate. So it says draw the C2 epimer. Okay, so C2 epimer. Well, we just number the carbons. 1, 2, 3, 4, 5, 6. And all we do is reverse the stereochemistry here. That's literally all you do. So I could even copy and paste this. Copy this and paste it over here. Like that. I'm just going to switch carbon number 2. I'm going to put the hydroxyl on this side, and I'm going to put the proton over here. Could anybody identify that one from the handout? Maybe yeah, maybe no. Does anybody have the handout further down? I don't know. Anyhow, this one is D-mannose. So D-mannose. And D-mannose. There we go. Give me a thumbs up if you follow me on epimers. Any questions up till now? Any like burning questions about carbohydrates? Because I'm more than happy to answer any questions that you have about carbohydrates or sugar chemistry in general. Okay, let's try another one. Let's try 24.28. I thought this was another good one. So 24.28. Oh, here's a cool one. You can do all kinds of wacky things with sugar chemistry questions. So 24.28 says you can end up with D-altrose or D-talose when okay, you take either of these and you treat them with sodium borohydride. So you can take either of these and treat them with sodium borohydride in water, and you end up with the same product. Same product. And it just says, explain this observation. So let's write down the structure of those two sugars. So we'll start with D-altrose. So I'll put it here. So D-altrose. And maybe we'll put D-talose over here. Keep track of them. So D-altrose, again, I just go over to the handout and I look up the structure of D-altrose. So 1, 2, 3, 4. And my D-altrose has a proton here, and then it's got 3 hydroxyls. So now we'll finish that out. There we go. And then D-talose has this. So I have my CHO, CH2OH. Then I have 1, 2, 3, 4. Oops, that's not very pretty. And then I have 3 hydroxyls up here, like this. 3 hydrogens here, like that. And whether I take this one and treat it with sodium borohydride in water, or this one and I treat it with, let me see here, like this. This one I treat it with sodium borohydride in water. But the reduction of the blue one, or this one, I end up with reducing the aldehyde to an alcohol. So I get CH2OH. And I have my other CH2OH here. And I end up with my 1, 2, 3, 4. So I have my hydroxyls like this. I'm going to run out of space the way I was trying to set it up here. Like that. But when I reduce D-altrose, so maybe I'll move it down here so you can see more clearly. Okay, so when we do this, so let me use a red pen for this one. We end up with something that looks like this. So we reduce the aldehyde to an alcohol. And we have this CH2OH. And now we have a hydroxyl up here. 1, 2, 3 hydroxyls like this. Now this is something I've not been able to figure out how to do, but if you compare the red molecule and the blue molecule, so if I take this and copy it and paste it, what you see is that these two molecules are identical to one another. Now, it might not look it the way they are, but if you take the one on the left and if you rotate it 180 degrees this way, can you see that it's the same as this molecule if you rotate it? Can everybody visualize that, or can anybody visualize that? You just spin that around like a top. So if you imagine this is your axis, the middle here, and then you just spin everything around 180 degrees, you get the same molecule. So something that I want you to be aware of, and I don't know if our book really goes into enough detail about it, but we could do the Drake meme on this one. When you have a sugar, rotating it is not a big deal. You can rotate sugars. So rotation, or like spinning, like I'm just showing you there, is okay. One thing you cannot do with a sugar is flip it. You cannot flip like a pancake. You cannot flip them upside down and say, oh, now I'll compare them. The reason why is because everything that's along this spine here, so to speak, or that carbon chain is going back in the page, and everything here is coming out on the page. So if you flip it over like a pancake, you reverse everything. You have something completely different. Whereas if you spin it around an axis like I'm showing here, then everything stays in the correct orientation. All right, there we go. So that was 24.28. I wanted to take a look at 24.32. So this is 24.32. It says, draw and name the product when each of the following compounds is treated with aqueous bromine, so that's bromine and water, at a pH equal to 6. These are the conditions for the oxidation of the aldehyde group to a carboxylic acid. So A says we're going to do it with alpha D-galactopyranose. So since we're making an aldonic acid, we have to have the open chain form. So I'm going to use D-galactose, like this. So I go into the handout, I look up the structure of D-galactose, and I draw that structure of D-galactose. So I have hydroxyl here, 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 and here, like this. So here are my protons, like that. And what I'm doing is I'm treating it with bromine and water at a pH equal to 6. And what that's going to do is it's going to oxidize the aldehyde. It's going to take the aldehyde to a carboxylic acid to make an aldonic acid. So let's draw the aldonic acid. I could just copy and paste this and just adjust the top. So let's paste this in here like so, like that. And let's put this in here. CH2, no, sorry, CO2H. It is a carboxylic acid. And that's all there is to it. Now it says to name it. It says for the name. So I'm not that concerned with naming, aldonic acids on the quiz. On the homework, maybe, because then you can kind of go look at the book and in case you forget. But the way you name it, if this is D-galactose, you replace the ose suffix with onic acid. So this would be D-galactonic acid, galactonic acid, like that. 24.34 is another good one. So 24.34, oops, 34, like that. This is where we get into the synthesis, the Kiliani Fischer and everything. It says draw and name the pair of epimers when the following aldopentoses undergo Kiliani Fischer. So this is the Kiliani Fischer reaction or synthesis. In A, we start with D-ribose, which is found in RNA, of course. Deoxyribose is found in DNA. So this is just plain old D-ribose. So let's draw that. All the hydroxyls are on the same side, like this. And then we do the Kiliani Fischer synthesis. So what's the Kiliani Fischer synthesis? First, we treat it with HCN. And this is where the new carbon comes from. So this is the new carbon that you're introducing, right? Because it's Kiliani Fischer is a chain lengthening. So chain lengthening, or growing, okay? It's getting bigger and bigger. So we're adding HCN. And then in the second step, we use hydrogen in that poison catalyst, palladium on barium sulfate. So all you do is you end up extending it by 1. Watch very carefully. You're going to have CHO, just like before, but now instead of 3 chiral centers, you've got 4. 1, 2, 3, 4. These ones, so this one, let me highlight them. So yellow, then we'll do blue, and then we'll do green, like this. These are the ones that are on the bottom, so they don't change. All those hydroxyls are going to be on the right-hand side, like this. Okay? But when you do the chain lengthening, you end up with epimers because you can't control the stereochemistry at carbon number 2. So you end up with a pair of epimers. Let me just copy and paste this to make my life simpler. Kind of. So copy, paste it. There we go. So in one of these, the hydroxyl will be on this side, and the other one is going to be on that side. So what do we end up with in this case is that we end up with D-allose. So this is D-allose, and this is D-altrose. And the way that I knew that was by going over to the handout. Another question I wanted to ask you is, let's say I draw glyceraldehyde, the simplest possible aldose that you can have. So I'm going to draw D-glyceraldehyde, oops, like this. Okay, so this is where the tree starts. On the first page of that handout is with D-glyceraldehyde. Could anybody tell me, is this R or S? Is the only stereocenter in here? And there's a very quick rule of thumb that you can use to tell if this is R or S. Okay, so if we look at that chiral center closely, we see that the hydroxyl takes first priority. The carbonyl carbon is second. This is third. And this is fourth. Remember that the hydrogen is coming out towards you, like it's trying to give you a hug, okay? Everything that's horizontal is going up. Everything that's vertical is going back into the page. So you go from 1 to 2 to 3, but the hydrogen is coming out towards you. So we're going counterclockwise, which is S, but we reverse it, and it's R. That means this stereocenter is R. The rule of thumb is all the hydroxyls on the right-hand side, if you have a hydroxyl on the right-hand side, it's R. And if you have any hydroxyl on the left-hand side, it's S. Okay, so that's the rule you can use. And I think I put a question like that in the homework. You don't even have to use all the Kahn-Ingold pre-log rules. You just look at it. It's on the right, it's R. It's on the left, it's S. And that's it. Very quick. I know I didn't teach you that in chapter 5 of Organic Chemistry 1. But if you're like, why didn't you show me that then? Well, at the time, I wanted you to learn how to use the Kahn-Ingold pre-log rules. So that's why we don't really explain that. And also, we don't look at a whole lot of sugars in Organic Chemistry 1. All right, let's take a look at another one. So this is 24.38. 24.38. And if I take it down here, it says when D-glucose, so D-glucose, undergoes a Vole degradation, so Vole degradation, followed by a Kiliani Fissure, the Kiliani Fissure synthesis, you get 2 epimers. So you get 2 epimers. And it says, what are those epimers? Well, let's take a look at the Vole degradation first. We haven't really taken a detailed look at that reaction. So Volga degradation, remember, you end up lose a carbon, so you lose a carbon. Whereas in Kiliani Fissure, we gain a carbon. So we're losing and then we're gaining it back. I'm sure that you could figure this problem out very quickly, but let's just go over it. I want to cover the Vole degradation with you. So here's our D-glucose, 1, 2, 3, 4. So let's fix this thing up. Oops, kind of close to the side here. There we go. So this is D-glucose. What we're going to do in the Vole degradation is 3 steps. The first step is to treat it with NH2OH, hydroxylamine. The second step is to treat it with acetic anhydride, that's for dehydration. And then the third step is an elimination using sodium methoxide. So sodium methoxide. So what's going to happen is we're going to lose the top chiral carbon, right? That's going to vanish. This one's going to go away for good. I mean, this one's going out in the waste. And the carbon that I have the red box around, that's the one that's going to become the new carbonyl. Let's draw that. So we're going to end up with CH2OH, like that, or CHO, I mean. And you have 1, 2, 3 chiral centers here. So we have a hydrogen, a hydroxyl, and another hydroxyl. So let's figure that one out. If you go over to the handout, that's D-arabinose. So we'll put here D-arabinose. And then we're going to do the Kiliani Fissure synthesis. So now we're going to add a carbon to it, but when we do, we're going to end up with 2 new chiral centers at that carbon as we grow the chain. Step 1 is HCN. Step 2 is the poison catalyst, palladium on barium sulfate. And so we end up with a pair of epimers. Let's draw them. Well, one of them, hopefully you can tell, is going to be D-glucose. So we have 1, 2, 3, 4. The bottom 3 are going to be identical. We haven't changed anything there. So we'll put all that in. Now I'm going to copy and paste this. And I'm going to put the hydroxyls on opposite sides. On this one, I'm going to put it over here. That's what we started with. That's D-glucose. And then I'm going to put the other one over here on the left. And we end up with D-mannose. D-mannose. And these two are epimers. And since they're both epimers at carbon 2, you would call them you'd call them C2 epimers, as a matter of fact. And there we have it.